Okay, Monday there's a midterm. Everything that I discussed today can't be part of the midterm, okay? Anything I will, not anything, but I will on Monday, I will cover another subject which is related somewhat. This will be not part of the midterm. So you have to have your reading assignments, you have to have read all the things that I told you to read in the syllabus. There was some kind of a confusion in the B space, what should be read and what should be not. If it says R colon, that's what you're supposed to read in the syllabus, okay? And there's a legend on the bottom actually. So we have been talking about equilibria, so you have reactants and you have products, and you can calculate the free energy at standard state, that's that little degree sign here or that nut up there. And at standard state, of course, everything is at 1 atmosphere and at 1 molar concentration. And that means you can get the direction from this. If delta G naught is smaller than 0, then it will go into that direction as it's written. And if it is in equilibrium then you have a K. A K is the equilibrium constant. That's the concentration over this divided by the concentration of the reactants. Don't forget, of course, the stoichiometric factors. They go in the exponent and so on. And with this K, if you have now the case, if delta G, if I would make more products, if the equilibrium, as I say sloppily, would lie on the right side, would lie with the products, or more correctly, its product favored, then you would have K would be, what would be? That would be a larger number than this here. K would be then larger than 1, is that right? So that would be this case here. Delta G would be 0, and K would be larger than 1. That's a spontaneous reaction, okay? So if you have delta G smaller than, larger than 0, delta G has to be smaller than 0, K is larger than 1. If delta G is larger than 0, then the reaction is not spontaneous in that direction that we have written it. And with this, you can deduce, if this gets into equilibrium, there will be some of this probably done here, made. If this is equilibrium, so you have more of this stuff here, more of the reactants and less of the product. So your quotient from this divided by this here, that equilibrium quotient, will be then smaller than 1. This would be the non-spontaneous direction. And then you have a very, very rare case when you could have K equals 1, and that would be delta G 0, delta G naught would be 0. Paintball, huh? Got it. Delta G naught would be 0. So, but this is a rare case that if K is 1, everything has to be the same concentration in order to have K1. So this is only one equilibrium condition. But generally you have to say delta G naught is not 0. The delta G naught is not 0 in equilibrium, okay? And now you have we had married delta G is minus RT ln K, and I derived this, excuse me, I derived this for you. And you can take the exponent, and you get K is the exponent of this here, minus delta G divided by RT. That's in the exponent, e to the minus delta G divided by RT. So this married K and G, and now we have all these cases we had that you have here. You have delta G is H, delta H naught minus T times delta S naught. Okay, that's all in standard state here. You can plot delta G over T, and we have done this the last time, and you need to be really versed in this. You need to know how these plots look like. For example, if you have delta H plus and delta S minus, this is negative, so the entropy gets within the reaction gets more ordered. It looks like this here, and then this looks like this. And I'm not going to go over this anymore now. You can see this is the slope analysis, and that's the intercept here. And depending on the delta H and the delta S, from this you get is it positive or negative, and vice versa. And there you have all these different cases. All right. So I have given you these graphs. Please study them and study also everything in the book that I give you to read. Now, as I said, the delta G naught is not 0 in equilibrium. K is in equilibrium. K is some kind of a constant. Can be larger than 1, can be smaller than 1, and it's related to delta G naught. But so if you have just the delta G without the degree sign, this is the free energy, the running free energy of a reaction. So you could write a delta G naught of a reaction, Rxn means that, and you can calculate what that would be for that reaction, okay? It's either smaller than 0 or larger than 0. It will tell you, is this a spontaneous reaction or is it a non-spontaneous reaction? But what is delta G? And this is without this end of state sign. What is that in equilibrium? So this is delta G. You can calculate anytime you can calculate a delta G. So you start your reaction, you have more reactants, and the reaction goes to products by itself. So what would delta G be? For that reaction to occur, delta G has to be smaller than 0, okay? And so this changes, the delta G gets larger and larger and larger when it's smaller than 0 until it is 0. And when delta G equals 0, then you're in equilibrium, okay? So there's a difference. So the delta G is essentially the free energy, but not at standard state of your products, minus the free energy of reactants, not at standard state. So you can, for example, I said this when we did these reaction quotient, you would do an analysis, and every time when it comes down here, somewhere is here is your equilibrium somewhere, it comes down, the delta G would be negative, so it gets larger and larger until it gets 0. So you would be able to calculate this, so the delta G of the product is increasing, and this is decreasing, okay? And with this, eventually it will be the same. Here you have the delta G of your reactants is much larger, that's why it's smaller than 0. And so in equilibrium, you have your delta G equals 0. So if that delta G is smaller than 0, that means you have more reactants, and it goes spontaneously towards the product, and it goes as long to the product it goes so long to the product until you have reached K. So in this means you have too many reactants. If you have too many products, over reactants is a smaller number, so Q is smaller than K. All right. So if you have reached delta G equals 0, and this is not delta G naught. Please put this in your head. Okay, not delta G naught. If you be asked when would that be in equilibrium, and they say delta G naught is 0, that's not in equilibrium. Okay, it has to be delta G Rxn has to be 0, and at this point then Q equals K. Okay, you are in equilibrium, then it's the equilibrium, and this is one fixed value for that specific reaction at one fixed temperature. When you, of course, you know how K depends on the temperature. We have discussed this also. Now, the other possibility is, of course, that you have delta G not as larger than 0, then it doesn't go in this direction, maybe it goes in this direction, okay? It's likely that it goes in this direction. In this case, you have too many products, and so if you divide the products, the sum of the products, G's of the product divided by the G's of the reactants, then you see that the Q is larger than K, and so it has to make more reactants until it gets to K, until this delta G is 0, and then Q is K. Are you with me? That's important, okay? All right, so now this is really the connection here. Delta G is delta G naught. That's the one you can get from your tables. And you have delta G and is RT ln Q, and this is the reaction quotient. And this is not in equilibrium. You can at any time you can calculate the delta G. At one point, of course, if it's in equilibrium, if this is ln K, then delta G becomes 0. So I can set this whole thing to 0. Okay, delta G is delta G naught. plus RT ln K equals 0. Remember, we had derived once, delta G equals minus RT ln K. Remember that when we did that? And this is exactly where this came from. And so remember, delta G in equilibrium, when you have K, is 0. Delta G naught is not 0, okay? That's the number that you get out of your table. This will be not 0. Now let me see if you understand, okay? We have delta G, and this is now, delta G is gives free energy for that reaction, all right? Not at standard state, as the reaction proceeded. And now you are in equilibrium here at 25 degrees. You have liquid water in equilibrium with gaseous water. You have a pot of water sitting here, okay? How many times have I said that? What's the pressure of this? First of all, you say, what is your K or your Q? What would be the pressure? Would that go in this direction spontaneous, or would this go in this direction spontaneous? So that's what you need to find out. And what is K? K is the equilibrium constant for that reaction. And since we're dealing with gas and with pure liquid, so it's probably only a function of the gas, the partial pressure of the gas. So why don't you think about this, and don't talk to each other, just give me the answer, please. It's a test for you, how hard you have to study. You got to start studying now. Somehow you're not getting out of the starting hole like for the other two midterms, I noticed. There's hardly any activity in the chat room. Or you understand everything. That maybe is also. Okay? Usually there's lots of activity in the chat room about 4 or 5 days before. So there was that midterm. It threw you off, I think. Oh, it made you see the light. Maybe that's a different story. Did I say spring break? No. Did I say spring break? No, I meant spring break. I said midterm. I meant spring break. What are you talking about? Okay. All right. Please have this right. Yeah, okay. Is that the right answer, you think? I think it's the right answer. Okay, I'm going to solve this for you because I need to move on. So at delta G, so obviously at 25 degrees, this is in equilibrium, but this is just the partial pressure. The equilibrium constant is the partial pressure of hydrogen, of water, okay? K equals P H2O. And what is that partial pressure? I said it how many 100 times? What is that partial pressure at 25 degrees? 0.031 atmospheres. Is that larger than 1? No, it's smaller than 1. Okay, so, okay. But it's larger than 0, isn't it right? It's larger than 0. So this should be the right thing here. There's only one larger than 0, so it goes in this direction. This is not spontaneous. Okay? It goes in this direction. Delta G is larger than 0. And with this K, as you just said, K is smaller than 1, 0.031 atmospheres. And this should be the... Oh, aha. Okay. So I said we are in equilibrium. All right? We are in equilibrium here. That means delta G equals 0. Nobody protested. But this is right. K is smaller than 1. But in equilibrium, delta G, not delta G naught. Delta G is 0. Did you get that? Even with my misleading you a little bit. Exactly. You were confused. That's a good thing. All right? So the right answer is this here, because it's in equilibrium. There we go, all right? So I have to correct myself. And how do I get back to the display? So this was the right answer. Even worse. Okay, all right. So I'm sleepy, obviously. But did you understand that? Do you understand that? Yes? Yes, when it says at equilibrium, then you know delta G Rxn equals 0, okay? Not delta G naught, okay? Delta G naught is not 0, all right? Delta G naught is delta G naught. Where we go here, let's see. At equilibrium plus RT ln K, okay? And this is 0 at equilibrium. All right, good, we have this. Now let me see if you understand reaction quotient. And don't let me trick you, okay? Which is the true structure at T1? So there is obviously, this is T1, it's the time, obviously, and this is a concentration. This is concentration of A, that happens to concentration of A, the concentration to B, you have 2 moles of this happens to concentration of B, and obviously this happens to concentration of C in time. So we talked about equilibrium before, and I've shown you, graphs like this. So now I'm here, something happened, Mr. Chatelier entered the room, and something happened here. So what is now, at this point here, is Q larger than K? Is Q equals K, that would mean equilibrium, or is Q smaller than K? Why don't you think about this and give me your answer, please? Ooh, okay, I will. Now this one is right there. C is right this time, okay? Why does it get green? Okay, it's yellow then. Okay, so what you see here, the concentration of this one decreases, and now it doesn't change anymore. This one decreases, it doesn't change anymore. The concentration of this here increased, okay? So that means here you are in equilibrium. Already here you're in equilibrium, and you can watch this in time as long as you want. You're still in equilibrium. But now you do something. You said, oh, I'm dumping in more reactants here. So now you dumped in more reactants. You brought it out of equilibrium with this Q equals not K anymore. And if you have more reactants here, the quotient is this here, the product divided by reactants, but you put more in there, so you have that number divided by even a larger number. That means your Q is smaller than K, okay? And you have more reactants, and this is the answer then. Now it will come back, if you have enough of A, it will come back to the equilibrium again, and will continue to go back down and make more C and combine to B. All right, so this is clear? No, it's not clear, but you need to practice this. So at the, we have talked about the kinetic gas theory, and I'm doing a little review now. A little review means that I speak with 100 miles an hour. And kinetic theory of gases, we have seen that these ideal gases, they consisted of identical, well-separated particles. So they are not very many if you have an ideal gas compared to a solid, for example. There's lots of room. They don't see that as much. They move in random directions with a distribution of speeds. So they have a distribution of speeds. They move in straight lines between collisions, and the collisions between the particles or walls are elastic. That means there's no loss of kinetic energy. So the energy is always conserved in this case. So we talked then about the pressure and energy and the temperature, and we had P times V, and I derived this here from on a molecular atomic basis. P times V was, this is for one is equals n times r times t, and this is what was for one molecule essentially. And so this is the average kinetic energy of one particle. The average, they have an average kinetic energy. They have different kinetic energies, these one particles, but they have an average kinetic energy, all right? And so the average kinetic energy per molecule is 3/2 times kb times t. Kb is the Boltzmann constant, and kb is r, that's the Renault constant, the gas constant, divided by the Avogadro's constant. So for 1 mole, the kinetic energy is 3/2 RT. So the kinetic energy of ideal gases depends essentially only on the temperature, okay? But the individual molecules, they have different kinetic energy, okay? So we then had defined this root mean square speed, the VRMS, I hate that, the VRMS, that is the square root for one molecule is the square root of 3 kb, that's the Boltzmann constant, times the temperature, times the mass here, okay? For 1 mole, we use 3R, that's actually essentially a constant, times T divided by the molar mass, okay? That's for 1 mole, and you take the square root out of this, that's how you get the root mean square speed. And here I've given you R, this will be given to you if you ask something like this. So essentially, the root mean square speed is proportional to the square root of T over M for 1 mole, okay? So this is a constant here. So we then have the distribution of species. If this is our speed or our velocity in meters per second, you have a distribution of species as a function of mass or as a function of temperature. Now, if this would be, for example, a low temperature situation or very heavy particles, very, very massive particles. Remember we had this table where we had these steel balls on there that were shaking. You had the small steel balls, they were moving around quite fast, and you had the heavier ones, they were not moving around that fast. Every now and then it started moving. And so that would be a low temperature. Now we can compare this same, let's see, we compare the same molecules with the high temperature situation. That would be a distribution like this here. They would have much more, quite a few of them have higher velocities, okay? And or if you compare a high mass to a low mass, okay? A heavy molecule or heavy atom to a light atom. So that would be the lighter atom then, okay? And so the root mean square speed is here. And if you have, for example, low temperature situations or you have a very heavy molecules, then the distribution of all of them is very close, or of many of them is very close to the root mean square speed. You see that here? This is all around here somewhere. But if you have a higher temperature situation or a light molecule situation, then you have a distribution. There's a lot of distributions away from the root mean square speed. You see that? There's many of them have a higher velocity than the root mean square speed. So remember that, okay? So then we talked in lecture 21, we talked about real gases, and real gases, they have a mass, they have intermolecular forces, okay? You know all the intermolecular forces? I hope you know them, okay? Water, for example, what intermolecular forces does it have? Hydrogen bond, what else? Dipole, what else? Dispersion, what else? What else? Ion, because water dissociates, okay? All right, that's water. All right, so you have these intermolecular forces. So any molecule has what force can generate what intermolecular forces? Dispersion, okay, good. So you have to correct for this, for the particle volume and the intermolecular interaction. Of course, they're not points without mass. They have mass and they have volume. So you have to correct your P times V equals N times R times T. You have to correct this with the van der Waals equation. And then we talked about phase diagrams. So no, we didn't talk about phase diagrams. We talked about real gases. And real gases behave ideal. What's the temperature when they don't behave ideal anymore? That's the critical temperature. Then you have phase changes, okay? You have phase changes, and you see this here. If you have a PV diagram, for example, you can compress that gas, and there's nothing happening with the pressure. So this is, for example, that would be at 100 degrees. You go from the volume, you go out of you compress it from the gas phase, you go into the liquid phase, and now you have the liquid phase. Of course, the liquid phase is very difficult to compress, you know? So you have a very steep dependence of the volume to the pressure. So you put all kinds of pressure on it, but there's not a volume change anymore. And this is, so the atmosphere is 1 atmosphere at 100 degrees. Is the water in equilibrium at 100 degrees in 1 atmosphere? Water with steam, is that in equilibrium? Yes, it is in equilibrium, okay? So, and then you have water and vapor at 25 degrees with a measure of 31/100ths of an atmosphere of gas on top of this. Is this in equilibrium at 25 degrees? Yes. If you have water at 25 degrees and you have 1 atmosphere of gas pressure on top, what will happen? What will happen at 25 degrees? The water will condense into water, okay? That the steam will condense into water. I'm sorry, the steam will condense into water. So this was the van der Waals equation. We have these adjustments for the pressure due to the collision and attraction of of the individual atoms and molecules, and you have also adjust the volume for a finite volume of molecules, okay? And I have shown you how this comes about. So this is the van der Waals equation, and there are these parameters A and B, and I have talked a little bit about those. Now then you have phase diagrams. You have a triple point. All 3 phases are coexisting at a triple point. This is a pressure-temperature diagram. Phase diagrams are always pressure-temperature diagram. This is the phase diagram for water. You see here there's a negative slope that helps us tremendously. That way the rivers are, and the lakes and bodies that freeze in the open, they freeze from the top. And as you know that the pressure increases the lower you come. So if you increase the pressure here, you have a solid. For water, that solid is called ice, as we know, okay? And so now you're going down in terms of depth. So now the pressure increases. Anybody knows how much the pressure increases per 33 feet or 10 meters? By 1 atmosphere. Every 10 meters, 1 atmosphere. You start at 1 atmosphere on the surface. At 10 meters, you have 2 atmospheres, 3 atmospheres, at 20, and so on and so on. So the pressure increases with this. The solid becomes liquid. So now you have liquid water. Very advantageous for us and for all life in aquatic life, because evolution would have to start over again every year. All right, if the rivers and the lakes and the bodies of water would freeze from the bottom up, so you'll never be able to ice skate because you have to wait forever till the river or the lake is completely frozen from the bottom. So now, when you have, for example, here, if I go, this is a solid, this would be ice, and so now I'm here at that temperature. That's a cold temperature, obviously. I'm here at that temperature.